Hey guys, I found this gem of a puzzle that made me smile when I found out it has two different ways we can solve it. A normal way and then a beautiful visual shortcut hiding in plain sight, using almost no calculations or words to get to the answer. Stay tuned for the end. When the side length of a square is 16 meters, what is the blue area? This problem is from the UKMT Maths Challenge. If you want to solve it, pause the video here and have a go. I'll start solving it in 3, 2, 1. Let's first get stuck in with the normal method, breaking the puzzle up into smaller, easier chunks. With this one, I think it's best to break down the puzzle into 3 separate squares, 2 smaller ones and a larger one, and apply the only length we know, 16, to them. For our smaller squares areas, our side length of 16 continues along the width of the square, so we can move our length up to see that each of the smaller diagonals is half of 16, 8. Now we know the length of the smaller square's diagonals. If we can find the side lengths of them, let's call them x. Our area is the side lengths, x squared. To find x squared, we can pull out the top triangle from this square, like so. As we've pulled it out from a square, the angle is 90, so Pythagoras' theorem applies to these side lengths. X squared plus x squared is 8 squared, so 2x squared is equal to 8 squared. If 2x squared is equal to 64, then x squared is equal to 32. Here we could root 32 to get x, but we're interested in the area of the square, which we've said is x squared, so we can stop here. Popping this back into our original puzzle, the smaller squares each have an area of 32. What's left is the larger square, which we haven't been told its length, which we need to square to get its area. So let's do that. Using what we already know, the fact that our smaller square's diagonal is 8 meters, also applies to its vertical diagonal, like so, given a square has rotational symmetry. As all side lengths of a square must be the same, the vertical height of the border square is also 16. Subtract 8 for the smaller square's diagonal height, and we get 8 as the side length of the larger square. If 8 is the side length, then 8 squared must be the area. 8 squared is 64. So we can pop this back in too. Summing the areas, 64 plus 32 plus 32, we get 128 meters squared as the blue area. The final answer. Wait, it's time for a visual solution. Now that we have the final answer, I was thinking we have squares within a larger square, regular shapes with plenty of symmetry. Surely there's some geometry we can exploit here to grab a really neat solution. There is, and it illustrates the beauty of geometry. Here's a visual solution. To keep track of where our smaller squares are going, let's turn them orange for now. First, break the smaller square into 2 triangles, then into 4 triangles, like so. Slot one of them into the bottom of the left gap. Take another triangle to fill in some more space. Likewise, take the other 2 triangles to complete the gap. We filled in one of our gaps with a square. If we repeat this for the other smaller square, we find we filled in the entire half of our border square with stuff that were once squares, and the rest is empty. There's now just one calculation we need to do, find the area of the border square and half it. The area of the whole border square is 16 squared, which is 256. Half of 256 is 128. 128 meters squared. The same answer we got before, simplified to just one calculation. Beautiful geometry. Thanks for watching Beat the Calculator. I hope you enjoyed solving this one, and see you next time for more logic and maths fun.